Yeah, I guess we can get going then. So thank you everyone for joining us once again. We're in week 3 now of the zkML Bootcamp, so it's really flying by and it's great to see so many of you back here attending once again. As I said today, we do just have the one session, but I'm sure it's going to be a really incredible one. We have Thomas Solberg joining us here from Ingonyama. So really looking forward to it. I hope you're all very active in the chat again. Please do drop your questions in there. But otherwise, Thomas, I'd love to hand over to you and please get things started.
Okay, great. Thank you very much.
Thank you.
So hello, everybody. I'm Tomer from Ingonyama. I'm a researcher in the ZK field. We're doing ZK acceleration. Today I'm going to talk to you about reproducibility in zkML. So first, what do I mean by reproducibility? Basically, a reproducible program is one whose output depends only on the inputs. That's what I mean when I talk about it. Sometimes this is also referred to as a deterministic program or deterministic algorithm. I'll also state it in another way, which is that I say that the program is non-reproducible if on different runs with the same input, it would yield different results. I hope that is clear, and if not, I'll just say what I'm not talking about when I talk about reproducibility. So I'm not talking about intended randomness. So usually adding some sort of a pseudo-random number generator is fine. I'm assuming that we can always fix the seeds for such random number generators, so we can run them in a completely reproducible way. It would also not interfere with any ZK proving. We can choose to use provable pseudo-random generators. So I'm just going to be setting that issue aside. One more thing I'm not talking about when I talk about reproducibility is pretty much the first thing you'll see if you Google reproducibility in machine learning. You'll see the reproducibility crisis in machine learning based science. So I'm not talking about that. That is an issue of research not being able to yield reproducible results, mostly because people are using machine learning programs to assist in their research, and sometimes people use different training for those models, and or they don't share their models, or they don't share their training data, and that leads to some problem with reproducing results. So I'm also not talking about that. Okay, so we know what I mean by reproducibility, and now the question is, why should you care, or who cares about that? And first, I want to tell you that this is not just a zero-knowledge related issue. Even when just talking about machine learning, reproducibility is an issue. There is a great talk by Duncan Riak from NVIDIA from 2019. I recommend watching it if you've never watched it. It's on YouTube, but mostly, and he's presenting this problem with reproducibility, talking about why it's an issue for the machine learning community, and pretty much enterprising finding solutions to this problem. I'm going to be referring here and there to his talk in my talk. It's a good talk, and it's a good to hear about it. But the main idea here is that this is already something that people in the machine learning community has been thinking about and dealing with for a few years now. And some of the reasons are that reproducibility is essential for debugging. Basically, if you have a bug in your model, you want it to be reproducible. If it sometimes appears, sometimes don't, maybe you won't even know you have this bug. Maybe it will be hard to find it. So it makes it very, very easier if your code is if your program is reproducible for debugging. Another issue is that this is a must-have for safety-critical application. If you have a medical machine learning model or an autonomous vehicle, you want to be able to predict what your model is going to be doing in certain situations, and you don't want surprises. And if you get different results at different times, then this might lead to safety issues, which generally are not wanted. So another reason why reproducibility is very important. Another thing is for measuring performance. So if your model is non-reproducible and your performance is somewhat probabilistic, and you're not you're measuring your performance with some variance, then if you, for example, make a certain change, you want to see if your performance increased or decreased. It's going to be much more difficult if you get different results every time. So all of those reasons are reasons why people in the machine learning community have already been talking about reproducibility and care about reproducibility in their models. And then comes the fact that this is also a zero-knowledge issue. So classical zk provers work with arithmetic constraints like R1CS, Plonkish constraints, GKR, and these are perfectly deterministic. There are ways to combine them with other proving methods, and we'll talk about that with other types of constraints. But the most efficient, the most simple constraints are just going to be arithmetic with integers, and this is entirely deterministic. So the more deterministic our code is, the more we are likely to be able to only prove it with arithmetic constraints, and that's a major plus for zk. And again, I'll say something about who doesn't care about reproducibility, and this is mostly with talks I've had with people, but people in the field of generative AI models, like LLMs or diffusion models, they're fine with having their code not reproducible. Basically, they kind of rely on a lot of probability in their code to get different results every time. Anyway, like you don't want ChatGPT to always give you the same answer when asked the same question, because you want it to feel more human, and and people, of course, are not reproducible. So so people in those fields generally care less about reproducibility. I don't think it means they can't also benefit from reproducibility, because, like I said, you can always use intended randomness. You don't need to add non-intended intended randomness over that. But in general, the feeling I've got from people in this field is that it's not really an issue for them. So this is something to be aware of. So especially if we are, if we want to come up with a zk prover for LLMs, we might find ourselves in the position where we can't expect the models to be more reproducible. So in other models, maybe there are solutions already for the model that would make the model itself more reproducible. And if we have a prover for such a model, we might have to incorporate those this non-reproducibility in our prover. Okay, so I talked a lot.
Thomas, sorry to jump in. I'm aware you can't see the chat. So we've had a question from Satya who asks if maybe you could elaborate on how reproducibility relates to explainability, which is obviously another issue with AI.
So what do you mean exactly by explainability?
Satya, I can see them typing in the chat.
Mm-hmm.
How the model did what it did.
Okay, so I'm not actually worried about that. So my main worry is going to be about how we prove inference or training in the model. Yeah, so this is not something I really worry about, or yeah, I don't know. I haven't thought about it.
Awesome, thank you. I'll let you know if any more pop up in the chat.
Yeah. Okay. So we talked a lot about what is reproducibility and why should we care about it. But let's now talk about where it actually comes from. Why do we even get non-reproducible models? So first, I will state the fact that floating point arithmetic is non-associative. And we'll see it by an example. So when I say associative, I mean if we take a certain operation, I'm going to use addition for my example, but multiplication is pretty much the same. So if we're calculating a plus b plus c, it matters whether we're adding a and b together and then adding c, or we're adding b and c together and then adding a. It matters for floating point numbers. And so I'll give you an example. So in our example, we're using numbers with a 3-bit mantissa. And we're going to take a and b, which are both equal to 1. And here we're representing 1 by 1.000. So those are the 3 mantissa bits. And then times 2 to the power of the exponent, which is 0. So this is how I represent 1, which is the value for both a and b. And then c is going to be 16. So 1.000. And then times 2 to the 4th. So what happens if I add first a and b together, 1 plus 1? I hope everybody can see that this equals 2. And 2 here is represented by the same mantissa with the exponent of 1. So now we have 1 times 2, which is 2. And now if I add c to it, I want to do 16 plus 2. And this is just going to be 1.001 times 2 to the 4. So this last mantissa bit has the value of 2, and the result is now 18. This is what we'd expect if we do 1 plus 1 plus 16. However, if we first add b and c together, now we're adding 16 plus 1, and we don't have enough room in the mantissa for this 1. So this 1 is going to be in the 4th bit of the mantissa. Our mantissa is only 3 bits. So 1 plus 16 here is just going to be 16. This is the default rounding for floating point or other rounding modes, but this is the default, and every rounding mode is going to have this this problem. So now b plus c is still 16. And if I now add again, if I add a, so I'm adding 1 to 16 again. Again, the 1 is outside the range of the mantissa. So when I first add b and c and then add a, I get 16. Well, when I first add a and b and then I add c, I get 18. So you see that floating point arithmetic is non-associative. The order of operations matter. And if now I perform this calculation in a multi-thread computation, so I let it run in GPU, then different runs may take different paths depending on which values are ready first. And that can lead to a non-reproducible code. So now, sometimes I will run the code, I'll get 16. Sometimes I will run the code, I will get 18. So here we have reproducibility. And actually, there's a little bit more to it. This is how the problem is usually presented when it's just a multi-threaded computation along with non-associativeness of a floating point. But I would say there's more. And that is, even if I run it on a single thread, or I manage to make certain path always be first, compilation optimizations can cause runs done on different hardware configurations to also take different paths. So I might compile this to run on a Mac, and it will choose one of those paths. So maybe on a Mac I will get 18, and then I will compile this to run on a PC, and my compilation will choose a different path, and then on the PC I will get 16. So I might have the same high-level code compiled into different low-level codes that are going to run and yield different results. And that's a problem for zk proving, because if now I take the high-level code and I arithmetize that, and I get a certain arithmetic circuit, and I use this to prove the code, and then I run the code on a machine that yields a different answer than my deterministic arithmetic constraint, I'm just not going to be able to prove running this code. So I will run the code, and it will not match my arithmetic constraint. So this is something that we also, in the zk field, need to take into account. We might have a code that on a certain machine is completely reproducible, yields exactly the same, but then maybe on another machine it yields other results. Also reproducible there, but then the high-level code is still something that I would call not reproducible. So this is where the reproducibility comes from. The reproducibility problem comes from.
Soma, we've had a question in the chat from Ramiro, who asks, would the reproducibility problem be solved if we found an efficient way of doing matrix multiplication over finite fields? And he says, at least for ML problems.
So as long as we're working with finite fields, we don't have a reproducibility problem. The problem starts when we're working with floating points. And we can have extremely efficient matrix multiplication on finite field, but then somebody is going to give us a model that runs on floating point, and the problem is there. If you can make the model run on finite fields in the first place, there's no reproducibility problem.
Awesome. Thank you. And then there's another question from Zane, who says, is this a problem in general with FP arithmetic in general? I.e., if you had a 5-bit mantissa, you wouldn't have this problem for this addition.
Sorry. So let me. Yeah. So of course, if I had a 5-bit mantissa, I won't have this problem for these exact numbers. But then I will just have the same problem if I add A and B and not 16 but 64. Yeah. So no matter what size your mantissa is, like the problem persists. The examples will be different. You'll need to have arithmetic with numbers of a wider range to make this problem appear, but it is going to appear. Basically, if you're using the full range of your floating point numbers, then this problem is going to appear.
Awesome. Thank you very much.
Okay, so there are, like I said, the machine learning field is already working on dealing with this issue, and there are certain solutions or certain fixes that we can talk about that come from the machine learning side without even mentioning anything about the zk side. So I'm going to talk about the main fixes, which are fixed point quantization, increasing intermediate precision, and deterministic operations, and I'm going to elaborate on each of those. So when I say fixed point quantization, basically, instead of using floating point arithmetic, I can quantize my numbers to fixed point, and then there is no problem of associativity. This is basically so working in fixed point is basically like working with integers or or in a certain finite field. I would say integers. It is the same as working with integers with a certain fixed scaling. The pros of this solution that this is already something that happens in the machine learning community. Many large models are now quantized, and even quantized to very small bit numbers, which make them very easy to work with. For example, quantization to ternary numbers, so plus or minus 1 or 0. Even some models today can be quantized to 1 bit and still perform pretty well. So this is not something the machine learning community is doing to help with reproducibility. Actually, it's something that they do to make models faster and more compact, and this is another pro of this approach. So when we used fixed point, arithmetic is going to be a lot faster, and storing the model is going to, this is compressing the model sometimes by a lot. However, this is not a full solution for certain reasons. One is that even when models even if we run inference with quantized models, usually the training is still done in floating point. So There is some research of doing training with fixed point, but for now, as far as I know, the model are much more performant if the training is done in floating point. So this can only contribute to a solution when we're working with inference and not when we're working with training. And also, a lot of the times, even if the weights are quantized, the input is not. The input might still be in floating points. So this is kind of a this is a partial fix. So we might multiply all the input with the fixed point weights, but then we're going to have the results still in floating points, and we're still going to do addition in floating points. So this is still only a partial solution, even for inference. And also this generally reduces model precision. So models are not going to be quite as good. Sometimes this reduction is small and manageable, sometimes not. So this is one approach that leads to some progress with when dealing with reproducibility. Another approach is increasing intermediate precision. And by that I mean, let's take, for example, a model that works in floating point with 32 bits. And then instead, perform calculations, run the model on a double precision machine. So floating point with 64 bits to generate our witness. Now, if we can ensure that all the non-deterministic discrepancies, all the errors occur in the extra bits, so that every time we truncate the double precision variables back to single precision floating point, then basically we have a deterministic 32-bit model. So this is a very strong approach, as long as the model is not so big that we can't control those discrepancies. But generally, 64 bits for a lot of models should be enough. So this is a quite generic fix. It preserves, maybe even increases model precision. However, it reduces efficiency by quite a lot. So now doing double precision arithmetic can be a lot heavier than doing single precision arithmetic. So our model is going to be less efficient. Okay. And the next approach is using deterministic operations, and this is actually the main thing that the machine learning community has been working on to make models more deterministic. And this is something that started with the talk I mentioned of Duncan Riak. He pretty much enterprised this idea of making machine learning libraries more have deterministic implementations. And I can give you examples of codes used to make running models in those libraries more deterministic. So there's a PyTorch example and a TensorFlow example, and also this expert cuBLAS. So cuBLAS is the CUDA linear algebra library, and it can also be forced to be more deterministic. And mostly, if we apply all these flags and tell our libraries to be deterministic, they're going to implement whatever algorithms we want for them in a deterministic way. And raise an error if there is no deterministic algorithm for a certain machine. And you can also find this GitHub by NVIDIA, which gives you the state of deterministic algorithms in all these libraries. This looks great. Now all we need to do is raise some flags, and everything is going to be deterministic. However, if you look at the TensorFlow documentation, you see that it says that to guarantee that your model operates deterministically, you must meet all of the following requirements. It tells you which flags to raise and so on, but then it also says use the same hardware configuration in every run. Okay, so if you remember at the beginning, when I told you that even if your model is fully deterministic on a certain hardware, but then you compile it for a different hardware configuration, and you get different results. This is a problem for zk provers. So even with those deterministic algorithms, this problem persists. So you might have a code which runs perfectly deterministically on a certain hardware configuration. Now put it on a different GPU, or even put it on the same GPU, but have it use a different number of threads, and it might give you different results. So deterministic operation are also only a partial fix here. Yeah, if we're arithmetizing the high-level code, and we don't know, we don't put knowledge of in arithmetization of the exact hardware configuration, this might not be a solution. A possible fix for that is to use lower-level code, and at Ingonyama, we've tried working with Llama CPP, which is an open source project which implements the Llama LLM in C++. And we have seen that if it's that if you run it in if you run a quantized model, then it would yield reproducible results across different GPUs, even different GPUs architectures. So the NVIDIA 3090 and 4090 have different architectures, but still this lower level code was managed to run in a reproducible way when it was quantized. You can ask, well, isn't just quantizing enough? But if you remember what I said before, sometimes when the weights are quantized, sometimes the inputs are not, and this was the case here. So when we only ran it quantized, when only running Llama quantized, we did not get reproducible results across different GPUs. However, Llama CPP, we did manage to get reproducibility for when we ran it quantized. So this is again some effort we see from the machine learning community. That is able to make code more reproducible, but this is still somewhat of a partial solution. And there are also further complications. So even so when you run a model that uses deterministic algorithms, and you evaluate it not over a single GPU, but over several GPUs in parallel, then those deterministic implementations will still might yield non-deterministic results. So as far as I know, there are no general solutions right now for running on multiple GPUs. I think for 2 GPUs there are, but more than that, the problem starts. And that of course is going to be a problem with very big models and with training, which are generally heavier than running inference.
We have another question in the chat which says, how much of the problem can be mitigated using statistical error correction approaches, and what unit of measurement is used to report on deltas between the different inference runs?
So as long as you don't care about zk proving, then maybe you can bound this non-determinism in some sort of a statistical way, and that might be okay for strictly machine learning applications, but for zk, if we like I said, for classical zk provers, we require determinism, and even if the error is somewhat statistically bounded, we're still going to have to take some measures to deal with this non-determinism to be able to prove the model. And this is actually the next thing that I'm going to talk about. So what happens when we get a model that is non-reproducible, and how we deal with that when we generate the zk proof. First, before I talk about that, I need to talk a little bit about generally how we deal with floating point in zk, because, like I said, this issue mostly stems from floating point. And here also there are a few approaches. One approach is to only work with quantized models, and basically assume that everything is quantized, everything is fixed point, and we can represent everything with integers. Daniel Kang's zkML, this is their approach. So this is one approach. Another approach is to truncate all variables to fixed point. So the idea here is you generate a witness using floating point, but then you truncate the precision to a certain precision fixed point after you've generated the witness. So this is kind of similar to how I described the idea of using with 64-bit floating point as intermediaries. So here we're kind of using the 32-bit floating point as intermediaries, but eventually we're working with fixed point witness with fewer bits. And this is the approach taken by Ezekiel and Circom. Another approach is to just prove the entire IEEE 754. This is the floating point. The entire floating point binary circuit. So you're proving floating point arithmetic exactly. I don't think anyone is using this approach. This approach would be highly inefficient, and I will give you some numbers to show that in a minute. Another approach is emulating floating point with software floating point. So so this is what RISC-0 is doing. They're representing floating point numbers as integers, which I think it can be up to 4 integers per floating point numbers. And then you're emulating the entire calculation of floating point with those integers. This also yields to some reduced efficiency. I will show you by how much in a couple of minutes. And another approach is doing arithmetic with range constraint errors. And by that I mean, for example, if we look at an arithmetic addition gate, which add A and B to get C, then we're representing each such addition as a slightly bigger circuit, where now we also have some error R. C now is going to be the same every time, and we're basically pushing the non-determinism into the variable R. But now we need to put a constraint over R and what range it could be in. And there are also a few approaches for that. So one is using polynomial constraints. So for example, if I know that I have a variable which can take values in a certain range, say here it's plus or minus 1 or 0, I can make a circuit that will prove that this is a solution to a certain polynomial, and that would put a constraint over the range of x. However, as you can see, the bigger the range, the higher the degree of this polynomial is going to be. So I'm going to be adding more and more constraints. Another approach, and this is taken from a paper by Garg and others called Succinct Zeros and Knowledge for Floating Point Computation. And they have another approach for proving inequalities. So for example, if I look at an integer k, which is larger than 0, there is a theorem by Legendre that says that 4k minus 3, or basically any number bigger than 0, which is 1 modulo 4, can be written as a sum of 3 squares. It's called Legendre's 3 squares theorem, and there are efficient ways to find those squares, and then I can just prove this equation, 4k minus 3 equals alpha squared plus beta squared plus gamma squared, with a second degree polynomial. Of course, if I also want to prove now that k is not just larger than 0, it's also smaller than another number, say a, I can then just take a minus k and prove that this is larger than 0. So when I want to prove a range over a number, I would need two such constraints. And the third approach would be using lookup constraints. So I can use lookup protocols such as PLOOKUP or CQ or whatever your favorite lookup protocol is, and constrain the range over that. As far as I know, there's no work right now implementing floating point arithmetic with lookup constraints. But I definitely think that would be an interesting work. And to compare efficiency a little bit, I know I'm a little over time, but I'm actually close to done. So is it okay if I take another 5 minutes?
Yeah, all is good. Feel free to carry on.
Yeah. Okay. Thank you. So this is a table from Garg's paper. And here they compare the efficiency of their work, which uses the three squares theorem. Over in the middle column, you see the result for the soft floating point, what I said that risk zero are using. And on the rightmost column, you'd see the result for implementing the entire floating point protocol, and they tell you how many R1CS constraints each of those approaches would need for either an addition or a multiplication gate. And they're showing this for either a 32-bit floating point or 64-bit floating point. So you can see that the IEEE solution would be highly inefficient compared to the other two. The soft floating point solution is more efficient by an order of magnitude. And their work is more efficient by almost by like half to a full order of magnitude over that. And of course, this is still a lot less efficient than it would be to just work with integers. Where with integers, you would have a single constraint per arithmetic operations. So this kind of gives you the feel of the different efficiency and where we at with working with floating point numbers. And up to here, I haven't talked about reproducibility. But in the reproducibility, the situation just extends to gates which we can think about as having more than one input. So in the so now when we're looking at A plus B plus C, we don't need to put in R just the rounding errors. We also need to put in R all of the variability of adding these numbers in different orders. And of course, the problem is bigger than just constraining R for three inputs. Because in machine learning, this is going to be applied for large dot product. So we have an entire row from the weight matrix and our entire input multiplied together, and we need to consider all of the range of the error that can come from non-determinism of this calculation. And we are going to have to put range constraints over all of that. And as we said, compared to our arithmetic constraints, these are going to be largely inefficient. So there is a solution there. It would just reduce the efficiency of our provers by a lot. And of course, if we under-constrain those errors, then this can lead to security issues. So a malicious adversary, a malicious prover, can engineer those errors to accumulate in a way that they might be able to change the outcome of the model and be able to prove false claims. So it is important to maintain these errors to be constrained. And then deal with the inefficiencies. So our main takeaway, and then I'll take any questions if you have them. So reproducibility in machine learning is a major issue, both with or without taking zk into account. There are steps taken to mitigate this in the machine learning sphere. And we should use those steps as design guidelines. We should make sure that our models are as deterministic as possible with these steps. However, always note that most of these steps focus on achieving reproducibility between runs on the same hardware configurations. And if we find ourselves in a way, in a place where we're arithmetizing the model on one machine and generating a witness on another machine, even models that appear to be very deterministic cannot be. So it's important to achieve reproducibility between different hardware configurations as well. So far, the zkML community have mostly avoided the issues. Like we said, we've mostly been working with fixed points, but this is and probably will continue to be a challenge for the zkML community. So this is why it was important for me to present it and kind of raise awareness for this. Yeah, thank you very much.
Awesome. Thank you so much to Toma for an incredible session. I'm seeing lots of people already in the chat saying thank you very much. So yeah, thank you very much for that. If anyone wants to find out more or do some research on Ingonyama, where's the best place for them to head? Are there any links or any tips you'd like to share with the cohort?
Yeah, so you can go on our site or on our GitHub, or if any of you is going to be at ZK Summit in Athens, I'm going to be there, and a few more of us are going to be there. So feel free to come and talk to us.
Awesome. Very cool. Yes, nothing like meeting face to face. I've dropped the website there. And afterwards as well, Toma, of course, if there's any other resources you'd like to share, we can drop it directly in our Discord channel, just to make sure everybody has access to those. So yeah, I'm seeing lots of thanks in the chat. So one final time, thank you so much for joining us. A really great session. And yeah, to our cohort, as I mentioned, there's no second session following this one. So you're all free now to go and enjoy your evenings or get back to work, depending on where you're based. So thank you for joining us. And yes, we'll see you all again tomorrow. Thank you, Toma. Have a good evening. Cheers.
Thank you too. Thank you, everybody. Bye.